have you ever actually stopped to wonder how your smart home really works? Think about it. You pull out your phone and instantly, the exact temperature of your living room, or you're watching a live feed of who's standing at your front door. It feels like magic, right? But behind the scenes, there's this massive, invisible web of what we call digital handshakes. These handshakes are constantly keeping your devices connected and, more importantly, keeping them secure from people who definitely shouldn't have access to them. It's a fascinating hidden world that we rely on literally every single day.
So welcome to today's Explainer. We're going to be completely demystifying the Internet of Things, or IoT for short. We'll be decoding the secret languages that keep our smart world functioning safely, taking a deep dive into the source material to figure out exactly how our devices are talking to each other.
Here's our quick roadmap for today. We'll start with the smart device security threat, then cover protocols and rules of communication. From there, we'll look at HTTP, which is the web standard, and then exactly why IoT needs a different protocol called MQTT instead. We'll break down how MQTT works with publishing, subscribing, and brokers, and finally wrap up with how we ensure quality and security. Let's just jump right in.
Starting off with Section 1, the smart device security threat and how we protect your digital home.
Because, let's face it, every single day our home networks are facing some very real threats. The second we connect a basic smart device to our Wi-Fi, we're essentially opening a potential door. Hackers can gain unauthorized access and actually take control of these devices. There's a terrifying example from our source material where hackers access the live feeds of smart home baby monitors and cameras. No way we want that. Then there's data interruption, where sensitive info is literally snatched right out of the air during Wi-Fi transmission. Devices can even get hijacked to become part of these massive malicious botnets, where they can get hit with malware injections. It's a pretty scary reality, which is exactly why we desperately need robust security.
Which brings us to Section 2, protocols, the rules of communication, or as I like to think of them, the invisible digital handshakes. To really understand how devices securely share information, we first have to wrap our heads around what a protocol actually is. Simply put, a protocol is just a set of rules for communication between two entities over the internet. The source material uses this brilliant dating analogy. Imagine two people are out on a date. If they both just start talking at the exact same time and neither one bothers to actually listen, well, that's probably going to end in a breakup, right? Computers are exactly the same way. Without a strict set of rules dictating who speaks, who listens, and how they should respond, the communication just completely breaks down.
And, for these devices to even find each other in the first place, they absolutely need an IP address. Think of an IP address exactly like your house address. If two houses on the exact same street had the exact same address, the delivery driver would be completely lost. They wouldn't know where to drop off your package. It works the exact same way on the internet. Every single computer, server, and smart device needs a totally unique IP address so the network knows exactly where to route the information without causing a massive traffic jam.
Moving on to Section 3, HTTP. This is the web standard, basically how the internet browses.
So let's look at how this HTTP handshake actually plays out in the real world. It's your classic client-server relationship. Let's say you want to open up a website. First, your browser, which is the client, looks up the server's unique IP address. Second, your client shoots over an HTTP request over the internet, basically asking for that web page. Third, the server receives this request, usually coming in through a specific open door called a port, like TCP port 80. And finally, the server processes the request and sends an HTML file right back as a response. Your browser renders that file, and boom, you see the web page. It's just a continuous, high-speed loop of asking and receiving.
But as we all know, things don't always go perfectly online. The server always talks back to the client using what we call HTTP status codes. If you get a 200, awesome, everything is okay and successful. But you've probably run into a few of these others. A 400 means you sent a bad request that the server just couldn't understand. A 401 means unauthorized, usually meaning you forgot your username or password. And then there's the infamous 404. We've all seen that one. It simply means the server couldn't find the page you were looking for.
Now, here's the absolute crucial point when it comes to security. Standard HTTP, it doesn't encrypt your data at all. It sends everything in plain text, meaning any hacker who happens to be listening in can just read it like a book. To fix this glaring issue, we use HTTPS, where that S stands for secure. HTTPS is really just the standard HTTP protocol, but with an added, heavy-duty layer of SSL or TLS encryption. This completely scrambles the data, keeping all those digital handshakes hidden from prying eyes.
All right, Section 4, Why IoT needs MQTT. Or, more specifically, the main problem with using HTTP for our smart devices.
Here's the thing. HTTP is incredibly heavy. It relies on massive data packets and keeps these heavy communication channels constantly propped open between the client and the server. If you tried to force that kind of heavy lifting onto a tiny battery-powered temperature sensor, it would drain the battery in no time. It's just way too much overhead. And that right there is why the Internet of Things relies on a completely different protocol called MQTT. MQTT is lightweight, it's blazing fast, highly efficient, and it sips power, making it absolutely perfect for these tiny, constrained devices.
Which leads us nicely into Section 5, MQTT, Publish, Subscribe, and Broker. It's kind of like the YouTube of the Internet of Things. In a fun fact from the source material, MQTT was actually invented way back in 1999 for the oil and gas industry. They needed a way to monitor remote pipelines over incredibly unstable, low-bandwidth satellite connections.
The way MQTT gets around this whole bandwidth issue is honestly brilliant, and it works almost exactly like YouTube. Right in the center of the whole operation is the MQTT broker. The broker is the beating heart of the protocol. Think of it just like the YouTube platform. On YouTube, a creator publishes a new video, YouTube receives it, organizes it, and then pushes that video straight into the feeds of anyone who's subscribed to that specific creator. MQTT uses this exact same publish and subscribe mechanism for data.
So, let's look at how this plays out in a real-world smart home setup. Step 1, your smart sensor reads the room temperature, let's say it's 72 degrees. The sensor acts as the client and publishes its little data payload. Step 2, it sends this to the MQTT broker under a very specific topic category, like living room/temperature. Step 3, your mobile phone app, which is subscribed to that exact topic, instantly gets the update from the broker. The crazy part? The sensor and your phone never actually talk directly to each other. Everything is routed through the broker, which saves a massive amount of battery life and bandwidth.
And finally, Section 6, ensuring quality and security, guaranteeing that the message actually arrives.
Because, sometimes networks drop out. This is where QoS, or quality of service, steps in. MQTT actually gives you 3 different levels to choose from, and it's all about trading absolute certainty for bandwidth. At most once uses the lowest possible bandwidth, but there is absolutely no guarantee the message arrives. It's basically a fire and forget method. Then you have at least once, which guarantees the message will get there, but it might accidentally get delivered a few times, so it uses medium bandwidth. Finally, exactly once is the highest guarantee. It ensures the message arrives perfectly, exactly one time, but it eats up the most bandwidth because of all the back and forth confirmations. You basically just pick the right level based on whatever limits your specific device has.
Now, to keep all this secure, MQTT architecture usually hides the broker safely behind a firewall, relying mostly on outbound traffic from the clients to keep the bad actors out. But what about devices that are even more constrained than a simple smart home sensor? We're talking massive smart energy grids or giant building automation systems. Well, the source material introduces us to CoAP. That stands for Constrained Application Protocol, and it's designed specifically for direct machine-to-machine or M2M communication over ultra-low bandwidth networks. It's essentially the ultimate lightweight security protocol for the absolute most basic internet-connected machines out there.
It kind of completely changes how you look at the devices sitting around your house, doesn't it? Just thinking about the sheer amount of invisible traffic, the complex rules, and these silent brokers working tirelessly behind the scenes just to securely deliver a simple temperature reading to your phone. It's honestly nothing short of incredible. So next time your smart home app updates in the blink of an eye, ask yourself, is that a heavy HTTP handshake happening, or is an MQTT broker hard at work? Thank you so much for joining me for this explainer. I really hope it sparked your curiosity to look just a little closer at the smart world around you. Keep learning, and I'll catch you next time.